I guess I'm audible, so can one of you just confirm thumbs up or something?
Yeah, you are audible.
Okay, thanks. Sorry for being late today. So welcome you all to this seventh problem solving session. So as you are well aware that in seventh week the course mainly discusses about the PUCCH chain, but before getting there I'd like to revise few basic concept about PDCCH chain. So compared to PDSCH chain, that is for data, can one of you point out what are the differences in the transceiver chain when it comes to PDCCH? Like what are the unique blocks we see in case of PDCCH chain? So let me write down my question here. So it's like refreshing our memory to just see in what aspect PDCCH is different from PDSCH. So anyone, which are the new blocks we see there?
So for the previous stage, we were using like APPC polar encoder, but for PDCs, we are using polar encoding.
Okay, that is nice. That is one difference. Very nice. What else? So for data we are using LDPC encoding, and for control information we are using polar encoding. Good enough. Are there anything else that is absent in PDSCH chain but is there in PDCCH?
So one more change is there, like for the previous stage, we are receiving multiple transfer block from MAC, but for PDCs, that will be only one.
Okay, but fine. But I'm talking about like when it comes to implementing the transmitter, let's say the transmitter chain. So what are the like what are the unique demands for like PDCCH, and that requires some new blocks maybe. Like for example, does user know where its control information are coming beforehand or not? Like PDSCH, of course, we assume that data is addressed to user, and as if user know beforehand where it's coming. But how about that information? Like how even user get that information? It's carried by PDCCH, right? In terms of rounding control information, and how user know about at which particular slot or position in the WebDM grid its information is coming. Okay, let me ask in a briefly other way. Like for example, when it comes to PDCCA chain, we assume that okay, these many resources are allocated to user. So as if user knows beforehand where its information is coming, but that information where its data is coming still need to be at the user end. So user receive that information in terms of in PDC via PDCCA chain. But how do user know that okay my control information is in this particular slot?
Just to do blind decoding.
Just to do blind decoding, very good. So but blind decoding also have certain rules, like otherwise like uh, there are some maximum number of attempts that is allowed. So for that, what are the measures being taken? We have to do blind decoding, that's completely fine, correct only. But blind decoding also has its own limits, right? It can do certain maximum number of attempts in a slot maybe. So how to address that, or
Yeah, it's
how
like
it, yeah.
interleaving has been introduced so that if it is not getting interconnected and you will be stop its decoding and it will be attend the new line, no decoding.
Okay,
That's how it
okay,
is.
okay, there is interleaving will comes into picture, absolutely correct, because that will facilitate early termination of decoding as you mentioned. So is there anything else required before this interleaving, or like you said that if the control information is not meant for the user it will terminate, but how do like how does the user know that its own information?
Like CRMA, if the PDCC system releases its own CRMA,
Okay,
that is the control, otherwise it is not terminated from another user.
okay. So it's like before that interleaving thing, some CRC scrambling block should be there, right?
Yes.
And scrambling happens, as you mentioned, with user specific some information you said CRNTI, correct? So I would like to use this as an anchor point. Let's say a user is entering the network, and in that scenario you won't have any CRNTI, of course. It doesn't really care about that data transmission. It only cares about at the moment about connecting to the network. In that case, how it will happen?
And the voice is that's why this happening for the network.
Your voice is breaking. Just a moment.
Repeat it again.
Is it okay now?
Yeah, yeah, fine.
Okay. So I was asking like when the user is, excuse me. So I was asking you all are able to see my slides, right? Or okay, okay. Okay, so what I was asking that when user is entering a network, it still needs some control information for letting the base station know that it's entered, and then for the scheduling will come later. That's okay. But at this point there is no CRNTI for it, like there is no user specific identity. So how does the transmission happens in that scenario? I mean, we have seen in earlier cases that okay, once the connection is established, fine, you have some user specific CRNTI, and then you have some user specific search spaces that consist of multiple code set. So okay, you will look at those places, you will do blind decoding, fine. But what about when the user is entering the network?
That time code set 0 and search space 0 will be coming into picture, and the DCI will be converted to SIRNT.
Okay, and what does SIRNTI represent, stands for?
So that will be used for system information IPA. That will be common for all the UAs. So
Okay,
those and all the UAs will be reading the same sequence from both the MIMO and the details purpose setting.
so this code set 0, what is being transmitted in code set 0?
Sequence.
uh, okay, master information block, fine, fine, master information block, good enough. Then, and what about this code set 1 thing that follows after code set 0? Okay, let's first talk about this code set 0. What information does it carry?
Sequence information.
uh, Sorry, can you just repeat once?
SID1. SID1.
Okay, no, I'm just trying to see like what kind of information it will be carrying, like codes.
Normally it will be like on its downlink common channel details and uplink common channel details. RAS related information. So that will be like that type.
Okay, okay, so basically it's like the search space information would be there, right? Where to look for. Okay, fine. And then comes the concept of code set 1 that immediately follow code set 0. What does code set 1 contains?
I think that will be used after RAR in config ACL. When we initiate the RAR process, it will be receiving RAR using the set instruction.
And what does that stand for?
RAR stands for your system.
Okay, so you're saying that remaining the code set 1 will contain like remaining system information and further scheduling that is required from the base station end, right?
Yes.
Okay. And what about this RDG to CC mapping for this code set 0? Is it interleaved or is it non-interleaved? And why is so? Okay, okay, okay. Can you just like repeat it once? I couldn't get it. Sorry about. Okay, okay, okay. And when we talk about this decoding thing, this there is something called PBCH, right? And that is the first thing user decode. PVCH. Okay, okay, okay. Got it. So we next talk about this uplink control information. Okay, let's go back to TCI for one thing. So DCI, if we talk about that, let me know that at what time frequency slot my data is arriving, and there is also this HARQ PDSCH this indicator. So this field is also present there. This is of like 3 bits if I am not wrong. So like what does it indicates?
It will indicate which PUCCH resource to use while sending the hardware.
Okay, so it basically tells you the slot, right? Like slot in the sense both in time domain and frequency domain. Where to send it, right?
This is the absolute value of P1.
This is the absolute value of
P1. P1.
okay, okay, okay. So basically in downlink control information, user get to know when it is going to receive its data in downlink, when it is supposed to send data in uplink, and also where to send this acknowledgement, right? Whether it received it properly or not. That is HRQ thing. So when it comes to this uplink control information, what is the maximum length possible? UCI.
1706.
So let me write it down. UCI max is less than 1706. Fine. So in PGCCH chain we have seen there is always one block, but when it comes to uplink control information, we have seen the polar encoder maximum can handle 1024 bits, right? So when the UCI length is more than 1024, how do we handle that in PUCCH chain? Okay, and that is unique from PDCCH, right? Because there is no need for segmentation. My maximum bit length is 140, so I am good enough with single one. But fine, in PUCCH I need segmentation here. So compared to PDCCH, what are the blocks that are not required here? Or okay, first let's talk about those which are not required in PUCCH compared to PDCCH. So I was asking that compared to PDCCH, what blocks are redundant here in PUCCH?
And only segmentation is new, everything is same.
Okay, so just a few minutes before you are talking about this CRC scrambling and CRC interleaver, are those also included in PUCCH?
Yes, subblock is there.
No, not subblock. I was like we are talking just before na when compared to PDSCH, the unique inclusion in PDCCH are CRC scrambling and CRC interleaver. These two blocks are there. So I was asking whether they are required here also in PUCCH. Because you mentioned that to facilitate blind decoding, to make blind decoding easy, we have this CRC scrambler and CRC interleaver block. So I was just curious that are those blocks still required here in PUCCH when it comes to uplink control information? Okay, and why so? Okay, so you are saying like when it comes to PUCCH, is base station who has already make the schedule where to transmit it and make the information available to user via DCI, and user is transmitting at that particular slot only, so there is no concept of blind decoding. Okay, fine. But we have this segmentation thing anyway. Is there anything else required uh, apart from segmentation? Okay, let's say let's focus a bit on segmentation part. So segmentation, how does it exactly happen? Like, are there some rules about that? That okay, if the maximum number of bits that goes beyond 1024, then only we segment, or something else? So if I call something like segmentation rule, so are there any rules that we need to follow for segmentation? Okay, let's say I'm writing one scenario when the UCI length, if I consider it A is like this. What we are going to do in this scenario? Are we going to segment it or not? Segmentation is not required. Okay, it actually there is a condition like there are two scenarios when the number of transmitted bits is more than what is the number, 1088, if I remember correctly, and another is less. So in this scenario, a number of transmitted bit is more than, this is a number of bits that are allocated for transmission is more than 1088, then actually I do need to segment it. So the idea is as follows, that intuitively we can see, since A is less than 1024, why should we go for segmentation? Of course we can transmit it like, it's like n is less than, n is between 360 to 1024, then we can just do, we'll write n bits, n is 1024, that is the maximum polar encoder output length, and I'll just repeat e minus n bits. So that's the intuitive thinking we can have as of now there, and why to segment it anyway. But it turns out that if you segment it into equal length, and then you do polar encoding, it will give you lower block length error or BLE error. So that is why in this scenario, when these two things are combined, then we go for segmentation. The number of resource bits that is allocated is more than 1088 and UCI length is between 360 and 1024. And there is another scenario, and can you just say what is the second rule, like what is the second scenario? It's kind of obvious.
Yeah, if it is greater than 1024.
Yeah, of course, if it is greater than 1024, then you will anyway need to segment it. So after you do the segmentation, then it goes to this CRC scrambling and interleaver anyway not required. Then we enter the polar encoder block and all that, and then we see something called right here. Okay, by the way, one important thing here, let's say if A turns out to be odd, the UCI length, so how do I address that? Because whenever we do segmentation, we know it has to be equal length. So if A turns out to be odd, that is not possible. So how we bypass that scenario?
Or the beginning will happen on 0.
The beginning you will do zero padding, okay, and you will make it even, and then you will do segmentation. Absolutely correct. Next come the, after you have this polar encoder output and all that, then you do channel interleaving thing. So what is the principle, like how do you exactly do that channel interleaving? This is a block that is not there, of course, in PDCCH. Let's say what goes at the input, as the input of channel interleaver is number of E bits goes there. So channel interleaving principle is something like this. You can draw a isosceles triangle kind of thing. It's good for visual interpretation part, how it happens. So basically what I'm planning to do, I have this E bits, a sequence of length E. I will write those bits in this order. Like basically I will fill up the first row like this, and then I will start writing from second row, and I will keep writing that onwards. So it's isosceles triangle. So of course this length here we consider it T, and we can see the each row is have one element, one bit less compared to the preceding row. So if we start from the very below, we have one bit here, then two, then three, and if we call the height T of the isosceles triangle, then we have basically 1 plus 2 plus 3 like that up to T. And since I have to embed these E bits in this isosceles triangle format, can you tell me any restrictions that I need to have here? Like in this summation they need to be equal to E or less than E or something like that. What should be the condition?
Greater than equal to.
Greater than equal to E. Okay. And this summation comes out to be
T into T plus 1 divided by 2.
E into T plus 1 divided by 2 greater than equal to E. So it can be equal to E, but most of the scenario it will be greater than E. So how do we take care of that? Because at input I have only E bits. So how do I fill the isosceles triangles in that scenario? Like for example my
Including null bits.
okay. So we are saying there should be T into T plus 1 over 2 minus E null bits. So that is there, like formation of isosceles triangle we talk about, and how to read it. I mean, what is the output of the interleaver? How should I do that? In input we write E bits row wise, and when it comes to take the output, that is the channel interleaver output, in what way I should read the bits?
Column wise. Read vertically and write horizontally.
Okay, okay. So basically I have to read the
Skip the null bits.
so okay, I'll find the read the bits vertically as the channel interleaver output, that I get it. Okay, so maybe in this you mentioned that there will be T times T plus 1 over 2 minus E null bits. So let's say my uh, uh, effective number of bits ends here. So from this point onwards I am starting writing null bits just to complete the isosceles triangle. So these blue circles are all null bits, and while reading it vertically, how do I do that? Like, do I keep the null bits or do I skip it, and like how should I do it?
You will not read the null bits, nothing is not there.
Okay, so basically
Whatever the cross you will not read.
okay, so basically you are saying when I am reading them in a column wise manner, that is vertically, I should skip those bits, right? Yeah, that's absolutely correct. We will skip those null bits. So at the output we will again have E bits, and since we did segmentation and perform the rest of the operations in a blockwise manner, be it polar encoding, subblock interleaver, channel rate matching, channel interleaving, uh, do I need to do something else like concatenation of any kind? Before mapping it to the grid? concatenation required or not?
Concatenation in what sense?
Those we have done segmentation, right? In UCI we have there is possibility there will be maybe one block, maybe two blocks. So from that point onwards, if we have like if this my UCI length satisfies the criteria we mentioned in the previous slide, we will segment it and we will have two blocks. Then we perform this encoding and rate matching and channel interleaving in every blockwise manner. And then do we need to concatenate or we still need to proceed with the rest of the processing in a blockwise way only?
I think concatenation will be required before getting the final output.
Yeah, so there will be another additional block, that is code block concatenation. And one thing, the code block concatenation can, that output can be odd, right? So but in the receiver side we again need to do deconcatenation, so the number should be even. So how do we address this thing?
By adding zero to between.
Yeah, again zero padding is our way out. Fine. So when we talk about DCI, we have already seen that is DCI format 00, that is for downlink scheduling, and 10, that is for uplink grant. Is there any similar concept when it comes to UCI, uplink control information, any format? If I talk about UCI format here,
Short format and long format.
okay, so you refer to this format 0 and format 2, right? I guess there are more formats like, okay, okay. So when you
Format 1, format 3 and format 4.
okay, so let us talk about the short format you mentioned, format 0. So what are the characteristics of this? Like how many bits is allowed, or how many symbols it spans, like that? We
It allowed 2 bits.
okay, here maximum allowed to transmit 2 bits, and how many symbols it can span? It can span again 1 or 2 symbols. And what is the immediate example we can see for this one? Like for format 0, what kind of information can be transmitted?
Ink on name.
.NET. Okay. while transmitting this ACK or NAC or to be more generalized sense, format 0, uh, do you use LDPC coding or polar coding or something else? Okay, but you remember like
If
to
it is 12-bit polar code, if less than 12-bit, then we use ad hoc codes.
yeah, correct. So we need to use some ad hoc code here, and can you give one such example that is being mentioned in course also? How do you do that? So if it's about ACK and NAC, how it's being transmitted? Are they transmitted in their raw form like 1 bit to 1 bit mapping, or there is some robust way of doing it, adding some parity bits and all that?
Yeah, I think some 1 bit is converted to 12 bits and then we are sending like this.
Okay, so let's say 1 bit to 12 bit conversion. And let's say I have a sequence, some arbitrary sequence, let's say minus 3 3 1 something of that sort, and what I'm transmitting e to the power j phi n over 4, something of this sort. Okay, and there are let's say 30 such sequence are defined. Yeah, we are for ACK, if we are transmitting let's say one kind of sequence, what should I transmit for NAC? Is there any?
Another sequence, 6, I think cyclic shift of 6.
Okay, the same sequence only but cyclically shifted by 6. And then I have to do some kind of QPSK thing, any modulation scheme that need to be applied, or on top of that? For example, in 1 bit UCI we done this sequence thing, and then I need to do some modulation scheme needs to be applied or not? So actually, what are the like this sequence is going to be? Is that a real sequence or some complex? It's e to the power j phi some angles, right, at the end of the day. So this 12-bit sequence is a sequence of complex symbols only. So no further modulation is applied. It's just those symbols are mapped on the PRDs or WebDM grid, and these are kind of transmitted. And what about that long format you are telling, that is let's say pick an example of format 2 maybe? Format 2 also transmits of course more than 2 bits, but it still spans 1 or 2 symbols. So what kind of encoding I should use here? If let's say the UCI length is between 12 and 1706,
Polar coding.
polar coding I'm going to use. one question that so when it comes to uplink control information, what is the reason for this kind of payload compared to downlink control information? Yeah, like I was saying, in downlink control information, we have seen the maximum number of bits is 140, and in uplink it can go up to 1706. So what is the reason behind almost more than 11-12 times increase?
Because of the hard
Okay, so you are saying that channel state information, right? Or channel quality information. And can you please elaborate on that? How is so? It's true, channel state information, but why channel state information can be that large? Like, yeah, like we'll come to that. We'll come to that. But I was just asking that why this CSI feedback or channel state information can be huge, right? For example, if I see, if let's say user have single antenna, then I just in bit confused about seeing the relation between high CSI feedback and user having single antenna.
single antenna and CSI feedback will be less now because RAM mechanism will be one only. CK will be 4 bits. Simultaneous means 4 bits, total 5 bits. Because when the number of antennas will be increased and the PMI will be coming in a big level.
Okay.
For beam measurement also L1RS and 360 measurement. There are 6 measurements.
Okay. And could that be also reason? Let's say user is allocated. Let's say user is observing very good SNR, or let's say it's a high priority user. So maybe I am allocating it the entire band for a particular slot, and there are multiple sub bands, right? If we talk about in terms of subcarriers or PRVs, so I am feeding back the. I'm basically estimating the channel for every PRV, like consider hypothetical situation, and feeding it back. So in that way it's also very high, right?
Yes, because you have to send the subband CQI for or subband CSI for every subband.
Okay.
If you have prepared 15, 16 subband, each subband 16 PRVs are there. You have to send at least 16 into 4 kind of things.
Okay. Correct.
In every
Correct.
subband you have to send some absolute inputs.
Correct. Exactly. So in this context, like what are the, from if we think from this perspective, in downlink control, in downlink control information, like what are the issues um, if downlink control information bits can be higher, like for example if instead of 140, let's say for some reason it's 1000, what are the issues? Like what are the possible issues? Maybe I was thinking.
So PCI bits will be more, then it will be very hectic for the unit because it is doing blind decoding for example. And
Okay.
if some bits are also got corrupted, then the entire DCI will be corrupted. So our targets will be minimum the DCI bits. only necessary, only we will be sharing noise information, so that decoding will be easier.
Okay. So till now we haven't talked about this MIMO transmission at all. So let us get a brief idea of that. So if I am considering a baseline case, that is a CISO system, we have single antenna at transmitter end, at receiver end I am also having a single antenna, and let's say the channel coefficient is H. You are transmitting some symbol with power P, and let's say consider the noise variance to be N naught at the receiver end. So if I talk about the SNR, what is going to be SNR in this case? That signal to noise ratio. You have a channel coefficient H, you are transmitting with power P, and the noise flow or the noise variance, you can call it, at receiver end is N naught. So if the channel coefficient is H, is absolute value square is the channel gain, that times the power you have transmitted with, and N naught is the noise variance. So this is the SNR you are getting for single input single output scenario. Now let us consider at receiver end I have two antennas, and here I am observing a channel H1, here I am observing a channel H2, and it's still transmitting with the power P. Here received signal Y1 is equal to, let's say what is transmitted is X has a power P, that means X squared is P, assuming X is constant. So Y1 is H1X plus N1 noise, and Y2 is H2X plus N2. So compared to single input single output case, what are the benefits can you say from having multiple receive antennas, because my transmit power remains same? So what are the benefits I am getting here? This is receiver antenna 1, this is 2.
The combined SNR increases.
Okay, so does the SNR increases automatically, or I need to combine it a specific manner? For example, I am given Y1 and Y2, let's say. So what do I do now?
You can use the MRC.
MRC. And what does MRC stand for?
Maximum ratio combiner.
Maximum ratio combiner. Okay. And what should I do to do this MRC combining? There should be certain weight, right? Like let's say if I use weight V1 to W1 and V2 with W2, that's what you mean by combining. V2 here. So what should be these V1 V2s? These are combining weights, right? And when you say maximum ratio combiner, what should be the weights V1 and V2 to it be MRC?
H1 conjugates over the norm of H.
Okay, so this weights needs to be conjugate of channels, right? That's what you meant. So So basically this will happen when receiver have channel information. So if I use, instead of V1, I am using H1 conjugate Y1 plus H2 conjugate Y2 plus N1, sorry, you will follow. Then I will have H1 square, H2 square, X plus N1, sorry, H1 plus H2, this is N1, H1 star N1 plus H2 star N2. So this is my effective noise part, and this one is my signal part. So my SNR now becomes H1 square, H2 square, whole square times P divided by H1 square plus H2 square. And of course we'll have N naught here, so it will be H1 square plus H2 square P over N naught. Fine. So what is the difference with the CISO case here? In CISO we'll have this thing, right, like absolute value of H square times P over N naught, and now when I have two antennas, I have absolute value of H1 square plus absolute value of H2 square times P over N naught. So what are the main difference here? My SNR increases, right, by another element. So if I extend it to, let's say, n antennas, if I extend to n antennas, we will have a sum of hi square, I runs from 1 to n times P over n naught, compared to just h square times P over n naught in CISO case. So if I consider this h values to be identical, essentially I will see some n times gain in SNR. Fine. Can the same things be repeated if I have two transmit antenna and one receive antenna?
Yeah.
Okay, so if I consider this scenario here, so you are saying MIMO gain is possible here also. MIMO gain is possible. But how is that exactly possible? For example, there cannot be any combining, right? Because you have single antenna at receiver end, so you have a one observation only. So So how do we achieve that?
You can use MTR at the transmit.
Okay. You mean MRT, right? Maximum ratio transmission.
Yeah, yeah.
Maximum ratio transmission. Okay. So you are transmitting the same signal X from these two antennas, but you are giving it a weight of, let's say, H star over H1, and here is H2 star over H2. You are multiplying X with this and transmitting over this antenna, that is H2 here, this is H1 here, so you are going to observe this kind of thing. But one thing we are maybe missing here, what are the crucial assumption that is being made here? See, when you have multiple receiver,
CSI is available.
okay, okay. So at transmitter side you need to know the channel, right? Otherwise the entire thing falls apart. It doesn't hold. Transmitter side CSI need to be known. Fine. So usually when we have the practical scenario, your base station is much more flexible in the sense it can have many antennas, and it doesn't have much power constant also. But when it comes to user is kind of very constant, be it in terms of power, be in terms of antennas. You cannot have many antennas at receiver, of course, because its form factor, that is your phone need to be small enough. So how do you achieve the MIMO gain in that scenario? Like, let's say you are only allowed to have one receive antennas. So to achieve the MIMO gain, what is required at base station end?
You can use transmit more power in those channels that have stronger channel gain.
Okay, that is actually the uh, same way of saying decoding, because if you are saying that H1 is much more strong than H2, then you are going to use the weight H proportional to H1 here, that is much more compared to the weight here. So essentially you are giving much more preference from whatever being transmitted here compared to here, so that way your power allocation is done. Okay, that I understand. But what I am trying to say here, at receiver end you have single antenna, and here we have seen that base station can have multiple antennas. So base station need to know the channel state information, right, to enable the MIMO gain. So how does it really achieves that? So basically it operates on TDD mode, that is time division duplex. That means if we are talking about a particular slot, let's say half, like hypothetically half of the slot is reserved for uplink transmission and half for the downlink transmission. So we are using something called TDD reciprocity. Reciprocity in the sense you are assuming that uplink channel is same as downlink. So what happens when uplink scenario, user is transmitting to base station estimates the channel, because it's more easier for base station to estimate because it has multiple antennas, and then it uses that channel state information to decode the signal for user in the downlink. I hope I am able to make my point here. So here the assumption is, the main point of reciprocity is your uplink and downlink channels are same. So in uplink, when user transmits something, it's much easier for base station to estimate the channel because it has multiple antennas. It knows the channel state information. Now it is using the same CSI to use this kind of precoding weights, and this is going to work because your uplink and downlink channels are same. Let's say if you work in FDD mode, that is frequency division duplex, what will happen in that sense, like what will happen in that scenario, your channel uplink and downlink channels are going to be different if you operate on FDD mode. So in that scenario, what is happening, your uplink is happening at a different frequency band. So whatever channel information you obtained here, you cannot use the same as the precoding weight here, because your downlink channel is from some other frequency band, and these H1 star and these H1 are not going to match in that scenario. So if you work in a FDD mode, that is frequency division duplex, this thing will fail because the reciprocity won't hold. Your downlink and uplink channels are not same. But if you operate in TDD mode, then your uplink and downlink channels are same. So whatever channel base station estimates in uplink, it can easily use the same in downlink to precode the information of user, and by this way your MIMO gain is possible. So base station operate in TDD mode. Reciprocity holds and achieves MIMO gain. So it's a good point to ask you, like let's say base station have a single antenna, and let's say another situation base station have 4 antennas, and the third situation base station have 16 antennas. Does the user which is equipped with a single antenna has any knowledge of how many antennas are base station is using for transmission? What do you think? There are 3 scenarios. One scenario, I am using single antenna from base station from transmission. Second scenario, I am using 4 antennas, and third scenario is I am using 16 antennas, and I am saying that user is equipped with a single antenna. So does the user know that how many antennas base station are using? It's not possible for user to know, right? Because all user is observing is this scalar channel, effective scalar channel, which is just a number. It can be because of a single transmit antenna, can be multiple transmit antenna, doesn't matter. What is going to observe is this scalar value only. So user is even not aware that how many antennas base station is using for transmission. So it's everything from the base station ends needs to be there to achieve the MIMO gain in case the user is equipped with a single antenna. So with that, let us solve few questions. So here we are asked to calculate the number of null bits in channel interleaving, and it says that PUCCH format 2 transmission and allocation of 10 PRBs over one WebDM symbol with a reference signal overhead of 1/2. So how do I calculate this? Anyone, like how should I proceed? First I have to calculate E, find the number of resource bits that are allocated. Okay, and how do I do that? Number of PRBs, find 10. At 1 PRBs, how many subcarriers? 12. Is there anything I need to be careful about here in this question when it mentioned that reference signal overhead of 1 over 2
into minus 6.
minus 6, and why is so?
The overhead is 1 by 2.
Overhead is 1 over 2, okay.
Like 2 symbol, 1 symbol will be used as a D.
Okay, so basically I have only 6 subcarriers for the transmission, fine. And anything else?
Yes.
Any modulation order? So nothing explicitly is mentioned, like so it's QAM only. So by the way, this is a good point, like when PUCCH is going to use UPSK and when it can use higher modulation scheme. Can one of you throw any light on that?
And the control information carried by PUCCH, we use whatever modulation scheme is in PUCCH.
Okay, so you are saying when I have nothing to transmit in the uplink, so basically only thing I transmit in uplink is control information, so then only I am using PUCCH, and in that case I am going to use QPSK or QAM. And when it turns out that I have both uplink data and control information to transmit, I am going to multiplex them both, and then essentially that PUCCH won't exist, it's only PUSCH, right? And then only I am going to use the higher modulation scheme. And when I say that multiplexing is happening, at what stage it will happen? The
Rate matching.
okay, at rate matching state, basically you will do that control and data multiplex. And by the way, when I say that I am multiplexing control and data information, are those both going through LDPC encoding or both through polar decoding, or how is that going to happen?
Both will go through LDPC.
Okay, okay, but I guess in the lecture professor mentioned that like they will go separately, like both PUSCH and PUCCH will be working, like whatever the data part will go through LDPC processing, and the control information will go through the polar encoding, and they will multiplex of course at the next stage, but the underlying they will go through different encoding process, if I am not wrong.
Maybe I missed.
Okay, I need to also see it, but most likely I remember him saying this, but I need to verify. Okay, I'll check that one. So here I am getting the number of allocated bits here as 10 times 6 times 2. Okay, so that is 120 here, and then what should be my next step? I have 120 bits that is being allocated to me for PUCCH format 2 transmission. How should I calculate that null bits that is required during channel interleaving? So it's about that isosceles triangle formation that we discussed of IT. So anything like t times t plus 1 over 2 we have seen, that needs to be greater than e, and we have to choose the minimum t that satisfies this. So t times t plus 1 greater than equal to 2 times e, or 240, the T minimum T that is going to satisfy that? Fifteen, right? Because if we have 15 times 16, we'll have exactly 240. So in that scenario, how many null bit I require?
Null bits will be 0.
So in that particular example, I'll require no null bits at all, because the isosceles triangle exactly matches with the number of bits allocated. What about this scenario? I have single input, I have multiple output. Single input, multiple output, I have 1 cross 2.
Why this? Excuse me.
You are asking the previous question why it is 0, right?
No. Channel is delivered. That's one.
In this question you are asking, right? Or
Yeah.
okay. So we have seen in the channel interleaving what we
Why
do.
is this in CSI? Why is this in CSI? First.
Uh, Sorry, can you just repeat once? Why?
The channel is delivered.
Yes.
Why is it in CSI? Why?
Why channel interleaver is required?
No, the
Sir,
please
again, why it is in triangular? Okay.
Yeah.
This triangular is like a geometrical interpretation for us. Like how the interleaving is happening. It's just what should I say? It's just one kind of like row column interleaving. Why exactly this shape? Yeah, there may be very different way of interleaving. Why this particular row column interleaving is chosen, that I don't have any knowledge as of now.
I think it is defined in 3GPP.
Yeah, like in 3GPP
They
specification.
did some simulation, and from there they for some reason they find this. Yeah, and I think it is mentioned in the lecture as well.
Okay. So it's basically they have come up with this particular way of interleaving by extensive simulation. This is giving them the best result. So that's why they follow it. Is that what's mentioned? Uh, So just to confirm from my end, like for example, like they are using this particular way of interleaving because they have reached this point by extensive simulation, and this interleaving kind of gives them the best results, right? Is my understanding correct? Or
Sorry, Saurabh, what you're saying?
yeah, like I was saying, like if I'm not uh, like I just wanted to understand, like for example, they have done extensive simulation and it turns out with this kind of particular interleaving they are obtaining the best results, right? Is that
Right, correct.
okay? Got it. Okay. this particular scenario, we are given a 1 cross 2 CMO system, that is single input. We have multiple output, multiple receive antennas, and this H1 is given as 0.3 minus 0.4 J, and this channel coefficient here H2 is 0.6 plus 0.8 J. So what should be the spectral efficiency for this particular system model? Uh, First of all, what is the expression of spectral efficiency? Okay, you are saying H square into P over N naught. Okay, and it is the SNR or AC, this one? Yes, this is SNR. Okay, correct, this is SNR. And how do I get AC? Yeah, like spectral efficiency. How do I write spectral efficiency? Log base 2 1 plus SNR, right? Okay. And the units are bit per second per unit bandwidth per hertz. Okay. And what we are getting here, log base 2 1 plus absolute value of H square, that is 0.3 and 0.4, that makes it 0.5 square plus 0.6 and 0.8, that is 1. P is given as unit signal power, noise variance is also given as 1, N naught is 1. So it's like log base 2 1 plus 1.25, that is log base 2 2.25. Most likely answer check once. Can you just repeat once? Okay, 1.17. Okay, my voice was cracking a bit from my end, so got 1.17 is the answer you are getting. Okay, fine. So the fourth one is the correct option. What about this question here? What are the reference signals that are used in downlink? Okay, so this, okay, so what are these things, by the way, this SRS, CSI-RS and DMRS, what are they basically? They are reference signals, of course, and they are kind of pilots, right? I mean, known at both user and station end. So I am just curious about their functionalities, like why 3 reference signals are required, like what are their purposes. Like if we talk about, let's say, SRS, how does it work? Like who transmit to whom this SRS thing?
transmit to RAM.
Okay, user transmits to denote B. Fine. And what is the purpose? Like
Link channel condition.
so basically you are saying that SRS is being transmitted from user end. It's like a pilot is user transmit these pilots, and base station estimates the channel, the uplink channel, of course. Fine. And okay, base station got the uplink channel, then it can use it to decode the user's information in the downlink. Fine. So that it can achieve the MIMO gain. Good enough. So what is the purpose of CSI-RS then?
Channel estimation in MCS.
So CSI-RS is transmitted by base station, you are saying. And what is the purpose? So
We will be estimating the channel at downlink and send us the
okay, okay. So you are saying that
MCS.
okay, so you are saying like base station will decode this CSI-RS and transmit to user, and user will estimate the channel condition basically and feedback the MCS. Fine. So what will happen if that CSI-RS is kind of, you say, removed? Like what will be the issue there?
RAM will be preparing the MCS as per the SRS specification. SRS channel.
Okay, okay, okay,
If SRS is not there. If CSRS is there, then the RAM has to go.
okay. So SRS will help this base station to estimate the uplink channel. CSI-RS will help this MCS feedback, that would basically allow the base station to know at what rate it's supposed to transmit. Fine. And what about this DMRS thing then? What is the use of it?
Before doing VDSS and USC channel estimation, we have to give up.
Okay. And I'm just trying to understand like why it is being required, because the station have the decoding information from SRS. It also have the MCS information from CSI-RS, so it basically knows at what rate to transmit and all. So why DMRS is still required then? Okay, okay. Okay, user will estimate. Fine. Okay, so DMRS is basically used by user, like for channel estimation purpose. Okay. The downlink reference signal option, as you said, is 1 and 3. So we are supposed to select the correct statement regarding code set 0. The first one is mentioned that it's configured by master information block or SIB1. Second says that user could use system information RNTI to address code set 0. Third is DSI format 10 can be scheduled in code set 0 for sharing PDSCH resource information. And fourth one is user assumed interleaved mapping for code set 0. So what are the correct options here? One is fine, okay. Second is fine, SIR interest common to all users. hard is okay, and fourth about user assume interleaved mapping for code set 0. So fourth one is not correct.
Fourth one is not correct because also the concept is interleaved mapping, but it is not UE specific. For all the UEs need to read code set 0, right? It is UE specific for one. UE has to read it, right? All are correct.
So in code set 0 is interleaved mapping only, right? Because it has to be spread across the different subbands, because see, basically we don't know about the channel condition for user, which band is good or bad. So basically the information is spread so that data can be decoded in a accurately in a stochastic manner. At least it can be ensured. If I do it in a non-interleaved manner, then there is a very good chance that wherever I am sending the code set 0, that channel condition may be very bad, so that entire information is kind of lost. So all the options are correct here. So we are given the output of rate matching block here, then only we are going for channel interleaving, and we are given of course the input sequence, and we are supposed to get the output sequence. So how should I calculate this thing? Like what is the one information that I need so that I could obtain the output sequence? Okay. If I calculate number of bits, then this is 5 here. This is another 5, 10. This is 15. This is 20. 25 here. 30. 35. 40. 45. 49 I am getting. Maybe I did some mistake or 5, 10, 15, 20, 25, 48. Okay.
मतलब 48 and take it in notepad
Okay. So it's 48 total. So I should calculate the T here, right? So you get T times T plus 1 greater than 80, and the choice of T should be 9, right? Oh, sorry. Thanks for pointing this out. It's 96 here. 6, then T will become 10. T will be 10, so that height is going to be 10. Height and width both for the first element, sorry, first row. So it will be 1 0 1 0 0 1 0 1 1 0. Second one, start from here, 0 1 0 1 1 0 1 0 1 1 1 0 1, then 1 1 triple 0 1 again 1 1 again triple 0. So I guess, yeah, rest should be null bits onwards, or I can just write it as n here. So we are having, if I read it in a 1 0 1 0 1, so third and fourth should be, one of them should be correct. They are correct up to 7 8 up to 8 bit, they are same. Ninth bit should be 1. So yes, third is the correct option. Can one of you please confirm? I guess third is the correct option because the ninth bit is 1 in that. Okay, thanks. So third one is the correct option. And then comes this question. We are supposed to select the uplink control information length for which segmentation is possible. So what should be our choices, or maybe what should not be the UCI length for which segmentation is done? What is the, or what are the odd mans out here? 256 is out of picture, fine. And okay, A need to be between 360 and 1024 when this is greater than 1088, and another one is much more obvious than this one, 1024 1706. Essentially we should look the number between 360 and 1706. Anything can be possible, but not less than 360. So 1, 2 and 4 are the correct options. So what is the CRC polynomial here that we are supposed to use for UCI bit sequence given as this?
Can you go to the previous question?
Yeah, yeah, sure.
Actually, in the lecture, the Broadcom 368, here also they mentioned 1706. Instead of 1024, here 1076 is the lecture.
Okay, which one? This first one you were saying, this one here? Actually, there are like two scenarios, like the this case is kind of obvious, right? I mean, if my UCI length is greater than 1024, of course I need to go for segmentation. And the first one is less obvious, but it also needs to be done when the number of resource bit allocated is more than 1088. So am I doing something wrong here, or
I'm checking again in the lecture script.
okay, okay, sure, sure.
Can you share my dashboard?
Yeah, sure. I guess nothing needs to be done from my end, right? You can share on your.
Repeat the question.
Oh, okay, okay. I got it.
So how we do it? We have
It's,
written 316, 1706 and 1013,
yes, yeah, got it.
I think it might be by mistake because in the first place it is written 360 to 1024. Now I am confused. Which equation is correct?
Yeah, I
This
think
one
the
or this one?
first one is most likely a typo. There, it should be like 1024.
Typo. Okay.
Yeah. And the second one is, of course, 1013. Yeah, it should be 1013 in the second scenario because I have not accounted for the parity bits. I am writing 1024 there. But it's actually 1013 because maximum parity bit should be 11.
So
So,
this is typo error.
yeah, yeah, yeah. This is typo.
This one is typo. Okay.
This one is typo. I have to correct here also
So
myself.
one more thing I noticed.
Yes.
So I just to answer Dennis' question, this is the probability release 15. This is how we arrive at the agnostic drivers.
The channel deliver thing. Yes.
Yes, yes, we can handle it. So in this one, 365. Right, so here it is written that we are using PPSK modulation. And modulation over video.
Okay. Yeah. So about this question here, we have a UCI bit sequence of certain length and we are supposed to find the CRC polynomial for it. So can one of you point out what are the different possibilities? first of all, let us see how many, what is the sequence length here. So if I pick the 5 here, this is 5, this is 10, this is 15, this is 20, and this is 3, that is 23. So sequence length is 23. Does it have any relation with the CRC polynomial that I am supposed to use? Bit sequence has any influence on that? Actually, it turns out if my bit sequence length A falls between 12 and 19, I am going to use a 6-bit CRC, and the CRC generator polynomial is a to the power 6 to the power 5 plus 1. Whereas when it crosses the number here 20 onwards, we are supposed to use 11-bit CRC. This generator polynomial has this expression D11, D10, 9 is there, 5 is there, and 0. So since the sequence length here is given as 23, we are supposed to use this generator polynomial. And of course, if in the assignment question if they ask what is the CRC bit, then you have to divide this sequence with this polynomial and supposed to use the remainder to find. But the polynomial you are supposed to use for this particular sequence of length 23 is this. If it's the bit sequence length comes out to be less than equal to 19, then we are supposed to use this generator polynomial, which will and output 6-bit CRC. So this is kind of trivial question after the things we have discussed. So what are the channels that carry UCI, uplink control information?
PUCCH and PUCCH.
So the first and third. First and third. Okay, so with this I would like to conclude today's session, and I will be happy to answer any question regarding this week's content. I will try my best to answer them.
So actually I'm having a question. Researcher. Why IM table is there? We are deriving it. On this one last
And last one. Here you are saying, or
no sir last week
okay, last week. Okay, last week. Yeah.
Normally we use a pi IM table, right? This is a generally we use a pi IM table.
Yes.
164. So in that 164, how you are calculating the value of incremental that I am having on that.
How you are using that? So let's.
How we are reading the table.
Okay. Okay. Can you share that table once if you have available with you now, or?
This I am joined from mobile.
Okay. 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 So let's say.
I can share.
Okay. Sure. Thanks.
I can
Thanks.
share. Just
how to read that thing, right?
Yes, yes, yes.
So these numbers you are seeing, like basically you first of all you need it in a row manner, like row wise manner. You complete the first row and then second row and third row, and the numbers basically denotes the position of the bits in the original sequence. So for example, if you pick the elements of the first row, that is 9. So that means whatever input sequence goes, the fifth bit in the original sequence should go to the ninth position. I mean, yeah, like that. So essentially what is happening, let's say you have a 50 bit sequence and your mother interleave pattern has a length of 164. So first of all you will calculate the number 164 minus 50 and it will come out to be something like 114. Then you will subtract the number 114 from every element of this 164 length sequence, and you will pick the only the positive ones from there, the only positive numbers, and that sequence is of the same length as your input sequence. Now you will adjust the position of your bits in your input sequence according to this pi minus h, whatever numbers is going there, like that. For example, if you see the picture, your pi minus h come out to something like 1, 4, 6, 10, right? So accordingly you will move the bits in your input sequence.
Okay. Got you, sir. Got you.
पहले शॉप में शेयर किया
Yeah, yeah. Thanks.
Is that like am I able to clarify it, or I need to explain in a
Got you, sir. Got you.
okay, okay, sure. So if we are not having any questions, then I'll conclude this session and we'll meet on next Saturday.
Sir, appointment available.
Um, Sorry, can you just repeat once?
Recording of this lecture will be available in this evening program, right?
Ha ha ha.
Okay.
Yes.
मुझे हैप्पी टीचर्स डे आई विल ऑन चैट विद ऑल सो प्लीज कन्वे टू प्रोफेसर एंड
Okay, okay, sure, sure. I'll convey your message. Sure. And I also asked about the slide thing, and he mentioned that like slides he cannot share. So, but I'll definitely carry your message like regarding the happy teachers day to him. Sure.
Oh, sir.
Yes.
Sir.
Hi, Dennis. Yeah.
Would you inquire about the master?
Okay, I'll ask the other course TAs, like if they have some plan regarding the same, and I'll inform you in the next session. Okay. Okay. So thank you all. I'm concluding this session now. Bye.
Thank you.
Thank you. Thank you.